Hello, everyone. My name is Will, and I'm a graduating Master of Quantitative Finance student at the Robert H. Smith School of Business at the University of Maryland. Before we begin, I'd like to thank Professor Stephen Heston for his support and guidance throughout the development of this video and the accompanying technical work. Also, this video has been reviewed and approved by Professor Heston. I'd also like to mention Professor Dylan Madan. Both are professors of finance at the Smith School. In this video, we're going to walk through Fourier inversion option pricing. The goal is simple. We're going to take one numerical method and apply it across three different models: Black-Scholes, Heston stochastic volatility, and the log-gamma model. So instead of learning three different pricing models, the focus here is understanding one unified approach that works across models of different complexity. Let's get started. So our game plan is very simple. We'll first talk about why Fourier inversion works. We'll start with the intuition behind Fourier inversion. Then we'll move into Black-Scholes, which is perhaps the most well-known option pricing method out there. It is short, it is elegant, it is easy to understand. So we'll start with Black-Scholes. We'll use it as our model 1. And through a very simple Excel spreadsheet, let's understand how Fourier inversion and option pricing come together. Then I'll talk about our second model, Heston stochastic volatility model. For our second model, I've also created a relatively short Excel spreadsheet to help you visualize how to implement Fourier inversion under the Heston framework. And then I have the third model, the Heston Log-Gamma model, and I also have an Excel spreadsheet for this. Now, as you can see, we're only using Fourier inversion and we're trying to price option under three different models. And we're trying to carry out these exercises in Excel. So think of this video as showing you how to use one pricing engine with three different models and all built in Excel. At the end, we'll compare all three approaches and wrap everything up. Before we jump into the models, let's start from the pricing problem itself. Now, let's remind ourselves how to price an option before we're getting to the more complicated stuff. Now, as shown in the first bullet point, the price of a European call option that pays the maximum of ST minus K and 0 at expiry capital T is equal to the current share price multiplied by P1 minus a discounted strike price multiplied by P2. This pricing formula for a European call option should look familiar to those of you who know about Black-Scholes. Under Black-Scholes, the P1 is written as N of D1 and P2 is written as N of D2 because we know that the log stock price follows a normal distribution, hence the notation of N for the probabilities. But in this video, since we will deal with other distributions as well, I will write the probabilities as P1 and P2. Now, if we know that the log stock price follows a normal distribution, and we also know that the normal distribution has a closed form CDF, we can almost immediately compute P1 and P2 and naturally the call price. However, in many models, we do not actually know the distribution of the terminal stock price in closed form. So instead of working with distributions directly, we switch to characteristic functions. And the idea here is simple. We will find a characteristic function. We will then implement Fourier inversion using the characteristic function. That will allow us to recover the probability. Then we'll use the probability to price our option. Now, first, let us look at something simple. In the Black-Scholes model, the log stock price follows a normal distribution, as shown here on the screen. That means we know both the distribution and the characteristic function explicitly. And I've written here on the screen the characteristic function for a normal distribution, but the key idea here is not that Black-Scholes is simple. The key idea is that even when the distribution becomes complicated, the characteristic function is often still available in closed form, and that is what makes Fourier methods so powerful. Now let's connect this idea to how we actually compute probabilities. And now we're looking at the core Fourier inversion formula. We can recover probabilities using Fourier inversion, where the probability is written as an integral involving the characteristic function. And this is where the characteristic function exists. So instead of needing the CDF, cumulative distribution function, we only need the characteristic function. But this still leaves an important question. Why does this approach work so well for option pricing? So let's step back and look at why Fourier inversion works. In Heston and Rossi's 2015 paper, it shows that we can replicate the call payoff like this. You might have noticed something very interesting. Inside this integral, now we have a sine function. And since the sine function is inside the integral, this is telling us that we can span the option payoff with a continuum of trigonometric functions. We can replicate the hockey stick payoff with a bunch of wave functions. Maybe like this. And with enough waves, we'll have something very close to a hockey stick. And excuse my lack of art talent, these two hockey sticks are supposed to look the same. So if we can create the same hockey stick, then pricing the result coming from the wave functions would just be the same as pricing the hockey stick. I have some graphs here to help you visualize the result. Let's first look at the graph on the left-hand side. The blue line shows the familiar hockey stick, whereas the orange line represents the Fourier approximation using only 3 frequencies. And if you want to graph this yourself, here is all the math you need. And as we see here, using only 3 frequencies, we are already getting something that resembles the hockey stick. Now let's see what happens if we include more frequencies. Let's say 100 frequencies. And that's exactly what I have on the second graph on the screen. As you can see here, the Fourier approximation lies almost exactly on the blue line. You can even see the blue hockey stick on this second graph. So let's remind ourselves what we're really doing here is we're trying to rewrite this payoff. And this payoff feeds into the pricing formula right here. This payoff gives us the hockey stick, while the right-hand side gives us this orange line and also this orange line. But we know if we increase the frequencies from 3 to 100, we will have a very, very good approximation of the call payoff, like this one. And to price this payoff, all we need to do is take the expectation under the risk neutral measure, and remember we have to multiply it by a discount factor. And that's it. That will give us the call option price. And once you see that, everything starts to connect. So we've just seen how the first two bullet points work, and then it's just a little bit of rewriting of the sine function, and that will help you understand how we get to the Fourier inversion of probabilities. Once we take the expectation of the payoff, the result that we get in the third bullet point becomes what we have here inside the Fourier inversion formula, and it sits in the numerator. Also, one thing to keep in mind, we do have some complex numbers here, here, and also here in the denominator. And in the Fourier inversion formula, here I'm taking the real part. Now that we understand the idea, let's move into some implementation. And let's start with our base case, model 1, Black-Scholes. In this model, log stock price is normally distributed. The characteristic function is straightforward. Here we have the characteristic function, and this is something that you can just look up. And also, n of d1 and n of d2 stand for probabilities under two different measures. So the mu's will be different, and I've written them down right here. If you've learned about Black-Scholes before, you should know that there's a sign difference here and here. And once we know our characteristic function, we'll use it in the Fourier inversion formula right here. By plugging in the two characteristic functions, namely f1 and f2, we'll be able to recover the probabilities that we need to compute our option price, p1 and p2. By the way, if you don't want to code this, you can always transform that into some trigonometric functions. This is what we'll have for P2. And remember, we're only taking the real part when the denominator is I times phi, or you can take the imaginary part, but over here the denominator will just be phi and there's no I. And now let's look at the small graph. Now over here, the x-axis is actually the phi value. As phi goes bigger, i.e. as frequency increases, the value of our integrand converges to 0. Now this graph tells us something interesting. Let's look at the integral first. It says to sum from 0 to infinity. But as I said earlier, we're trying to do this in Excel, and I also said the spreadsheet is going to be short. That means I'm actually not adding all the way up to infinity. That also means I have to pick an upper limit for the integration. And I'll show you how I do that later in this video. And the upper limit better be here or even here, because the integrand value at these points will all give me something very, very close to 0. Overall, my goal is to add up all these integrand values up to a point where adding up more integrand values are essentially just adding zeros. By not adding all the way up to infinity, this is how we'll be able to build a short spreadsheet using less data and price an option much faster. And here's a little bit more math for P1. Its characteristic function looks a little bit different, so the mathematical representation will be a little different, but the intuition that we get from the graph is the same. Also, the Fourier inversion formula does not change, so we're still doing the same thing. We're still adding up all these integram values up to a point where adding more integram values are just adding zeros. Make pricing a lot easier. And inside the red box, we can see some pricing results. As you can see, the call price derived from the Black-Scholes closed form solution is 8.35, and the Fourier inversion method tells us 8.35 as well. Now let's look at P1 and P2. We can clearly see that the discrepancy is extremely small. Overall, these pricing results look great. We have confirmed that the Fourier inversion method can give us accurate results. And now I'll show you how to put everything together and compute the integral numerically. At this point, there are two practical questions we need to answer. First, how do we approximate this integral? And second, how do we implement it in a simple practical way? Let's start with the approximation. Here we use the midpoint rule, which is a form of rectangle integration. The reason we use this method is simple. It converges very fast. In fact, under fairly mild conditions, we can transform the integral in a way that gives us extremely fast, essentially exponential convergence with the rectangle method. In practice, what we're doing here is already very close to that setup. So that's why we get highly accurate results with very little effort. Also, that's why we do not need more complicated numerical techniques. Now let's look at how this is implemented in Excel. What you're seeing here is a grid that represents the discretized version of the Fourier integral. Each row corresponds to one evaluation point in the integration. In the first column, we construct the frequency grid using midpoint spacing. This will help us avoid the singularity at 0. Next, we compute the characteristic function at each of these points. Because we're working with complex numbers, we split everything into real and imaginary parts. So you'll see separate columns for the real part and the imaginary part of the characteristic function. Then we build the integrand. This corresponds directly to the Fourier inversion formula. Once we have the integrand values, we simply sum them up across all rows, multiply by the step size, and apply the prefactor. That gives us the probability P1 or P2. Now, the second practical question is where to stop the integration. In theory, the integral runs to infinity, but in practice, we truncate it. As you can see on my spreadsheet, I have a parameter that I call big. This is what I use for truncation, and typically we set big equal to 6 or 8. And just remember, big is not a precise mathematical boundary. It's just a rule of thumb based on a simple idea. For a normal distribution, 6 standard deviations is already almost infinity. So instead of trying to find an exact cutoff, we just choose a value that's large enough so that the remaining contribution becomes negligible. Now, there's one subtle detail in how the spreadsheet is set up. In my implementation, I scaled the argument of the characteristic function by a volatility measure. So the actual frequency phi used inside the characteristic function is the grid value divided by a standard deviation. That means even though the grid runs from 0 to big, the effective frequency, the effective phi, inside the characteristic function is scaled. And that's why my upper limit appears as big divided by the standard deviation. But the key takeaway is that big is just a practical truncation parameter. It doesn't need to be exact. As long as it's large enough, typically 6 or 8, the method produces very accurate results. So putting everything together, what the spreadsheet is doing is very simple. It builds a grid, evaluates the characteristic function at each point, constructs the integrand, and sums everything up. And because the midpoint rule converges so quickly, even a small number of rows, like 6, is enough to get highly accurate option prices. Alright, now let's move to Heston's stochastic volatility. In this model, volatility itself is random. So the distribution of log stock price is no longer normal. But the key idea still holds. We still have a characteristic function. Compared to Black-Scholes, obviously the Heston model is more complicated. But what we do here is still the same. We still plug the characteristic function into the same Fourier inversion framework. And we can see this in Heston's 1993 paper. Here is the characteristic function. The function itself is longer than the Black-Scholes, but let's look at equation 18. The Fourier inversion framework is still the same. And here's some technical note that I created to help you understand the characteristic function under the Heston framework and how this framework computes the standard deviation via cascading ODEs. And something here is different from what we just saw in Black-Scholes. Remember, in Black-Scholes, we have one standard deviation that applies to P1 and P2, but over here, we're getting two different standard deviations. So when we compute P1 and P2, make sure to use the right standard deviation. Obviously, for P1, we'll just use standard deviation 1, and for P2, we will use standard deviation 2. Also, we're going to create a short Excel spreadsheet. So we'll have two different upper limits, and those upper limits are given by big over standard deviation 1, and that's what we use for F1, and big over standard deviation 2, we'll use this for F2. Now, in theory, we could compute the exact standard deviation of log stock price, but in practice, that level of precision is not necessary. Instead, we can use any reasonable measure of volatility to expiration. For example, say under the Heston framework, something like the square root of theta times time to maturity or the square root of the initial variance times time to maturity already works very well. Hence, the key idea is that we only need a rough sense of the scale of the distribution. We're not trying to measure volatility perfectly. We just need enough information to set the integration range appropriately. And because the method converges so quickly, this rough approximation is more than sufficient to produce highly accurate option prices. And on my Excel spreadsheet, I have 10 rows of data points, and we're integrating all the way up to 8 standard deviations in our original space. And based on the probabilities that I found, the option price is 1.03. And when I compare this pricing result against my benchmark price, which we've done in Mathematica, the difference is negligible. Now let's move on to the log-gamma model. This model introduces skewness, kurtosis, and jump-like behavior, making it more flexible than Black-Scholes. So in this model, we have a new parameter called the delta. It controls jump intensity, skewness, and excess kurtosis. And as delta approaches infinity, the distribution converges to a normal, and the formula converges to Black-Scholes. And also, it's important to note that this log-gamma model is nested within the variance gamma model published by Dilip and Don, which I have in my reference. And remember, the first step is to find the characteristic function of our distribution. And we can simply look up the characteristic function of a gamma distribution, which is given here. And this is where delta is. And the Heston's log-gamma model assumes the log stock price has a rescaled gamma distribution. So we're going to need a couple more parameters here for the scaling. And this is for computing P2 and this is for P1. And since P1 and P2 are scaled differently, they will each have their own standard deviation. We'll have standard deviation 1 to calculate F1 and P1, and we'll have standard deviation 2 to calculate F2 and to eventually find P2. In this example, again, we're using only 10 rows of data points. Once again, in Excel, we use the same Fourier inversion engine to compute option prices. But notice here, it does have a closed form solution. This is similar to Black-Scholes, which also has a closed form solution, because we know the log stock price under Black-Scholes framework follows a normal distribution, and over here, we're saying that log stock price follows a gamma distribution. So it does have the ability to produce a closed form solution, which serves as the benchmark price for us to compare our answer against. As we can see here, the closed form answer is 60.6094, and according to our Fourier inversion method, the answer is 60.60938. Notice how few data points I'm using here. I'm using only 10 rows of data. And the integrand here and here, they follow this very simple form. So computing the option price using the log-gamma model plus the Fourier inversion method is actually pretty simple. Now let's compare everything. Across all three models, the Fourier inversion framework, the numerical integration, and the grid structure all remain the same. What changes is the characteristic function and the assumptions about the distribution. Let's wrap everything up with a few key takeaways. The first idea is this. We're really using one engine across three different models, whether it's Black-Scholes, Heston stochastic volatility, or the log-gamma model. The structure is always the same. We start from the characteristic function, apply Fourier inversion, recover probabilities, and then compute the option price. So the entire pipeline is characteristic function, to Fourier inversion, to probability, and finally to option price. Now, the reason this works so well is that the characteristic function is the right object for this problem. The call payoff can be represented as a sum of trigonometric functions in log price. And since trigonometric functions are closely related to complex exponentials, taking expectations naturally leads us to characteristic functions. That's why everything fits together so cleanly. Another important point is that A more complex characteristic function does not mean more complex numerics. Even when we move from Black-Scholes to Heston or log-gamma, the numerical procedure stays exactly the same. We're still using the same grid, the same midpoint rule, and the same integration structure. Only the characteristic function itself changes. Next, the midpoint rule with a relatively small cutoff, something like big equals 6, 8, or sometimes even 10, is already enough to help us get highly accurate results. This works because the method converges very quickly, so we do not need a large number of grid points to get highly accurate results. Finally, neither big nor the standard deviation needs to be estimated precisely. Big is just a rule of thumb truncation parameter, and the standard deviation can be any reasonable approximation of volatility to expiration. Just remember, we're not trying to measure these quantities exactly. We just need a good sense of scale. And because the method converges so quickly, even rough estimates are more than sufficient. So overall, Fourier inversion gives us a very powerful and very practical framework. It lets us handle different models with the same numerical engine while keeping the implementation simple and efficient. That's all I'm going to say about the Fourier inversion pricing. And before I wrap up, I'd like to once again thank Professor Stephen Heston for his guidance and feedback. His insights were extremely helpful in shaping the technical content and the presentation of this material. Thanks for watching. Hope to see you in the next video.